Variance of standard distributions. Variance for a Poisson distribution. This will be the first application of that previous formula for variance. Suppose a random variable x has a Poisson distribution with parameter mu. What we'd like to show is that the variance of x is mu, identical to the expected value. We start by finding the expected value of x times x minus 1. That is, of course, the sum of the values x times x minus 1 times the probability function for the Poisson with parameter mu. And the first thing we do in this calculation is ignore the first two terms in that sum, the terms corresponding to x equals 0 and x equals 1, because in both of those cases, the value x times x minus 1 is 0. So we replace the sum from 0 to infinity by a sum from 2 to infinity. And the next step is to expand x factorial in the denominator as x times x minus 1 times x minus 2 factorial. And now it becomes evident why it is we wanted to calculate e of x times x minus 1. We have a convenient calculation between x times x minus 1 in the numerator and the same term in the denominator, leaving us with a sum, x goes from 2 to infinity, of mu to the power x minus 2 divided by x minus 2 factorial. You'll notice that we got mu to the power x minus 2 by removing mu squared from the summation and putting it out in front. We did the same with the factor e to the minus mu. That summation now can be rewritten by a change of variables as the sum j goes from 0 to infinity, mu to the j over j factorial, and you will recognize that as the expansion of e to the power mu. It's the Taylor series expansion that we used in developing the Poisson distribution. We're left with mu squared e to the minus mu times e to the mu, or simply mu squared. The expected value of x times x minus 1 is in this case mu squared. And since the variance is that plus mu minus mu squared, we get mu squared plus mu minus mu squared, or mu. For a random variable x which follows the Poisson distribution with parameter mu, both the expected value and the variance are identical. They're both equal to the parameter mu. Here's an example. Suppose about 1 person in 100,000 is hit by lightning in a season. Let x be the number of people in a town with a population of 10,000 people that are hit by lightning. Find the expected value and the variance of the random variable x. Well, x, the number of people in the town hit by lightning in a season, has a binomial distribution on the assumption that there are 10,000 individuals, each of which has the same probability, 1 over 100,000, of being struck by lightning. And all of these so-called trials are independent of one another, hence the binomial distribution. But we also know that when n is large and p is small, we can approximate very precisely the binomial with a Poisson distribution. The parameter of the Poisson, mu, is the expected value of x, which is n times p. In this case, 10,000 times 1 over 100,000, or 0.1. We also know that the variance of x is mu, also 0.1. Variance for binomial distribution. If x is a random variable with a binomial distribution, parameters n and p, then the variance of x is n times p times 1 minus p. To show this, we use an argument very similar to that for the Poisson distribution. We begin by finding the expected value of x times x minus 1, writing that as a sum over x goes from 0 to n, x times x minus 1, times the binomial probability function. As before, we can begin that sum at x equals 2. As before, the first two terms in the x factorial in the denominator cancel with the terms x times x minus 1 in the numerator. Now we break off the terms n times n minus 1 and p squared from the numerator in this expression, and factor it outside, move it outside the summation sign. We're left with the sum x goes from 2 up to n minus 2, choose x minus 2, p to the power x minus 2, 1 minus p to the power n minus x. This sum should look familiar. In fact, if we were to replace x minus 2 by j, then this would turn out to be the sum of all of the probabilities for a binomial distribution with parameters n minus 2 and p. And that sum, of course, the sum of all of the probabilities for a binomial n minus 2p, that's 1. So we're left with n times n minus 1 times p squared. So once again, to get the variance, we take the expected value of x times x minus 1, which we just obtained, add mu, subtract mu squared, but mu is n times p. So replacing mu by np and doing a little algebra, we end up with the variance of a binomial equal to n times p times 1 minus p. Here's a review example that you should attempt on your own. Suppose x follows a binomial distribution with n equals 10 and p equals 0.4. Find the expected value in the standard deviation of the random variable 4x plus 3. The first thing you should do toward solving this problem is to note that x has a binomial distribution, and we know the expected value and the variance of a binomial. The expected value is n times p, in this case 10 times 0.4, which is 4. And the variance, n times p times 1 minus p, 10 times 0.4 times 0.6, which is 2.4. Now we're in a position to calculate the expected value of 4x plus 3. The expected value of a linear function is the linear function of the expected value. This becomes 4 times e of x plus 3, 4 times 4 plus 3, which is 16 plus 3, 19. What about the variance of 4x plus 3? Remember that the addition of 3 doesn't alter the variance at all. So we're left with the variance of 4x. Factoring the 4 outside and squaring it, this is 4 squared times the variance of x. 16 times the variance of x, 16 times 2.4, which is 38.4. The standard deviation, of course, the square root of the variance, is the square root of 38.4. Review problem 2. Here's a somewhat more challenging problem. The manufacturer of cell phones ships them to retailers in cartons of n cell phones. Profit per cell phone is $59.75, less a shipping cost of $25 per carton. So we can write down what the total profit is. It's $59.75 n minus $25, where n, remember, is the number of cell phones in a carton. To promote sales by assuring a high quality, the manufacturer promises to pay the retailer whenever there's a defective cell phone in the carton. And in fact, as punishment for having a large number of defectives, they pay the retailer 200 times x squared, where x is the number of defectives in a carton. The retailer then assumes responsibilities for repairing or replacing any defective product. We suppose that cell phones are produced independently, and 5% of the cell phones are defective. How many phones should be packed per carton if we're interested in maximizing the expected profit per carton? Again, you can pause while you work out the review problem, and we'll give you a solution in a moment. Solution. We suppose that n cell phones are packed in a carton, and x of these were defective. X, the number of defectives in a carton, therefore, has a binomial distribution with parameters n and p, where n is unknown, but p is 0.05. So the expected value of x is n times p, and the variance of x is n times p times 1 minus p. We need to know the expected value of x squared, which we can obtain by taking the variance of x and adding the expected value, the quantity squared. The variance of x, n times p times 1 minus p, turns out to be 0.0475 n. The expected value of x, the quantity squared, becomes n squared times p squared, or 0.0025 n squared. So we now have an expression for the expected value of x squared, in terms of the unknown quantity, n. We also know that the net profit per carton is 59.75 n minus 25, minus the penalty we pay for defective items, which is 200 times x squared. So to get the expected profit, we take the expected value of this, equivalently replacing x squared by e of x squared. After a little bit of algebra, we end up with a quadratic function minus 0.5 n squared plus 50.25 n minus 25. We want to maximize our expected profit over our choice of the value n. And it's easy to check to see that the maximum of this quadratic function occurs at n equals 50.25. However, Since we're unable to put a quarter of a cell phone in a package, n is required to be an integer, we'll choose the value n equals 50, the integer closest to this maximizing value. Of course, as you know, you could check the maximum value by differentiating the quadratic and setting that derivative equal to 0. Setting the derivative equal to 0 and solving generates the value n equals 50.25. In conclusion, in order to maximize profit, cell phones should be packaged in cartons of around 50 phones each.